in the last class. So we have considered a rectangular section made of steel. Which has strength yield strength Fy and these dimensions d and d, and then we have plotted moment curvature curve. It was linear initially, then the first yielding occurred, then it becomes flat. Okay, so these 2 points we have my, we have calculated how much? Ze into Fy, my dash and phi by dash 2 epsilon y by d, and this was 2 epsilon u by d. Okay, and then we replaced it by equivalent bilinear curve like this, where this moment my we have taken is equal to mp, and that is zp into Fy. Okay. So can you tell me what is the corresponding value of phi y? Simple. It's a linear relationship. So it will increase from phi by dash in the proportion of my by my dash. So how much is my by my dash? My by my dash, both we have calculated yesterday. How much is Zp? We have calculated Zp also. Vd square by 4. And how much is Ze? Vd square by 6. Okay. So how much will be phi y if I know phi y dash? What is the ratio between Zp and Zy? अरे भाई 6 and 4 में ratio होगा 1.5. So my is 1.5 times my dash. Okay. So phi y will also be 1.5 times phi y dash. That is 3 epsilon y by d. And then we can calculate mu phi as phi u divided by phi y, and that is 2 by 3 epsilon u over epsilon. Agree? And that is 2 by 3 of mu epsilon. You agree up to this point? Then I told you to think about the effect of axial force. If we apply axial force also, what effect it will have on the moment curvature curve and then on ductility, curvature ductility. So let us say that this same section, let's say this is a cantilever, it is subjected to a force P and electrical force Q, okay, and the cross section here is P by D, okay, and this P I told you as 25% of its axial capacity. Let us apply. So this, let us apply 0.25 of DDF. So you can see that now the neutral axis will not be at the mid depth, at the center of the section. Okay, it will shift towards tension side. Let's consider the first case when the strain in the extreme fiber is epsilon y. Let us say this depth of the neutral axis is x, or you can also say xu or c, whatever you want to represent, and then this will be d minus xu. So you can see that both the fibers are not reaching the yield point simultaneously. If it is subjected to compressive force, then the fiber of the compression side will reach the yield strain first. The tension side will reach the yield strain later. Okay, because there has to be a linear relationship. If you take this as epsilon y, this will exceed epsilon y. So here this epsilon t, this will be equal to epsilon y into or divided by xu into d minus xu. And you can see this is less than epsilon y. So first yield will take place on the compression side. Can you now plot the stress diagram? How the stress diagram will look like? Yes.
How can you say that the first yield find the stress in compressive side?
Okay. First of all, we have said that the force acting is compressive force.
Yes.
So to balance the compressive force, here the equation will be C minus T equal to P.
Yes.
So C has to be greater than T.
Yes, compressive.
Then only it will register the compressive force.
Yes.
And if C is greater than T, the neutral axis or the area on the compression side has to be more.
Yes.
Then only C will be larger than T.
Yes.
Okay. So the neutral axis has to be on tension side. It will not be at the center. It will be on the tension side. That means xu is greater than d by 2.
Yes.
And if xu is greater than d by 2 and strain diagram is linear, you can say that for any value of epsilon, the compression side strain is going to be more than the tension side strain. And if compression side strain is more than the tension side strain, so compression side fiber is going to yield first. So that's why at first yield we are considering the extreme fiber on compression side to have yield strain. And then the strain on the tension side will be less than the yield. So the strain on compression side has reached epsilon y at the extreme fiber. On the tension side, it has not yet reached epsilon y. So in this case, can you plot the stress diagram? How the stress diagram will look like? Same section which we have considered yesterday. So only difference from yesterday is that now we have applied axial force. Earlier it was pure bending. In pure bending it was symmetric section. Steel has identical stress strain behavior in compression and tension, so everything was symmetric. But when we apply axial force, it will be no more symmetric.
It will be like this plus this. Stress. This is
Plot the stress diagram. Finally, what stress diagram you will take? See, stress strain curve has to be followed. We call stress strain curve as the constitutive law. Constitutive law means material has to follow it. So it has to follow stress strain diagram. You know the strain, you know the stress strain diagram. there you read what will be the stress. Yes. So when strain is up to yield strain or less than yield strain, okay. So you can just do epsilon y this pattern. So up to epsilon y, the stress strain curve is linear. So this was the stress strain curve which we have used, the simplified stress strain curve. So up to epsilon y, and your epsilon c is somewhere here, because that is, sorry, epsilon t, not c. Epsilon t we have seen there is less than epsilon y. So that will be somewhere here.
Yes.
So for both sides, it is still in linear range only. So the stress diagram will be linear only. It will be Fy here, and here it will be Ft equal to Fy. Same linear relationship. It will follow as the strain.
Plus.
Okay.
Plus effect of compensating force.
That is included here. Once you have got the strain is due to bending, compression, tension, whatever you have. Finally, the strain is like this. So, stress will depend on the strain. How much strain has it? So, all that compression, tension, etc., everything is included.
No sir, due to compression, all fibers are subjected to equal strain, and due to that equal strain, multiply by modulus of elasticity will be strain, stress profile will be.
You do that, from there also you will get the same thing.
Same thing not get. I get Fy plus this 0.25.
But you cannot apply axial force over and above Fy, because then the strain will exceed epsilon y. We are considering the strain not to exceed epsilon y. So that condition we have considered. If you want to apply axial force or strain due to axial force over and above that, then the section has yielded. Then I will exceed that point. So strain has to be restricted up to epsilon y. In such condition, how much axial force, and axial force is constant, how much additional bending moment I can apply. That condition we are checking. Okay. If you are applying only axial force, how much will be the strain? Suppose you have applied axial force so large that the section has yielded under axial force itself. Okay. So then it will not be able to take any more moment. We are trying to get the moment when this axial force is already applied. So if axial force is applied, 0.2 VDFy, this axial force is applied, what will be the strain? 25% of that capacity I have applied. So how much strain will be there under axial load alone? Not here, epsilon. That will also be 0.25 epsilon y. Okay. So due to axial force, it is 0.25 epsilon y. How much additional you can take? 0.75 epsilon y to take care of the moment. That moment you have to determine which will limit the strain within 0.7 f. Okay. Suppose axial force itself you have taken BD 2 times BDFy. What will happen? It will fail. Yes. Strain everywhere will be more than epsilon y. Suppose you have taken BDFy, then whole section will have strain epsilon y. There will be no capacity left to take any moment. Okay. So we have taken P is equal to 0.25 BDFy, so that the strain due to axial load is only 25%, and still 75% capacity is available which can be utilized to take care of moment. Okay, so now using this, can you calculate C? Now C will no more be equal to T. Can you calculate C? Yes? 1.3 F by dd. 1.3 or 1 by 3? Oh, sorry, 1.3 or 1 by 3? 1.1 by 3. How? You have to just get the area of this triangle multiplied by B. So this will be in terms of axiom. Okay. So that will be 1/2 into Fy into B into axiom. Agreed? And how much will be T? 1/2 into Fy d minus xu over xu into B into d minus x. To satisfy equilibrium, C minus T is equal to P. That is you substitute C and T, you will get a quadratic equation in xu. You have to solve that. Alternatively, you can do iterations. If you don't want to solve quadratic equation, I just solve the quadratic equation. That will give you xu. That's the computer access. Alternatively, you can do iterations. Assume different values of xu, calculate C and T, okay, and equate C minus T equal to P. So, if you want to do iterations, what value of xu you will like to take? From where you will start? You can start from anywhere from 0 to infinite. So which value you will like to take? More than dy. So it will be between dy to and d. So assume the value between dy to and d. Okay. Calculate C and T. And iteratively you can find xu, or you can develop a quadratic equation here. Do that. Solve that quadratic equation. You will get the value of x. Yes. Sorry, can I explain what? Okay, you will assume a value of xu. That value you can assume between dy and d. Yeah, but this is in terms of xu. So this xu I have to solve. Xu can be solved either solving this quadratic equation, or this equation can be solved identically. Like assuming a value of xu, putting here and seeing whether you are getting equal to this or not. And then you can adjust xu till it comes out to be equal. So both ways you can solve. Yeah.
This value is accounting effect of both P and Q.
Right. Actual force and moment force.
We do not have this.
No. Because we are not calculating the value of Q. Okay, or sorry, we are not calculating stress under any given value of Q. We are calculating the value of Q under that strain. So the strain we are fixing here. Suppose value of P and Q was given. Then you will calculate the strain under P and strain under Q, you will superimpose. Okay. But here what we are doing? We are fixing the strain and then we are calculating Q. What is Q? M divided by L, or M is Q into L, length of the cantilever. Okay. So we want M versus phi here. So we are calculating value of M and phi corresponding to first G. So that is epsilon 1. So strain is fixed. Now you have to back calculate Q. So once you calculate XU, then you can calculate. You have got 0.5 D. How it is possible? Achha, this is the equation. Okay, this is only the equation. Not anything. So this you can solve by making quadratic equation also. Yes. 2 by 3. So you can calculate M and phi at this depth of interaction. Okay. You have calculated axis calculated here. A moment axis का value अच्छा, keep in mind in case of axial force, okay, the axis of bending is important. Remember, so you are not taking it about neutral axis. You will take moment about centroid axis. So, in case of bending alone, when C is equal to D, you take moment about any axis. That is okay. You will get the same result because it is a couple. But when you have applied P also, it is no more a couple. C and T are not equal. C and T are different. In that case, about which axis you are taking a moment, that is important. And as we discussed in the first semester, the axis about which we are taking moment is same as we have done in design and analysis. Okay, so the axis would be same while designing and while performing analysis. And that is centroidal axis. So we have to calculate moment about centroidal axis. So XU has been calculated as 2 by 3 D in this. Just check. Even if you are not able to solve the quadratic equation, substitute the value of XU equal to 2 by 3 D and then see C minus D is equal to 0.25 FI BD or not.
For D,
For
D also we are getting two values. D equal to this much and D.
No, D you can't get two values. D is fixed, D is given dimension. So D you don't have to evaluate, you have to evaluate XU. You will get the value of XU, not D. D is already given. you will first calculate center, that will be 2 by 3 of 2 by 3d. So 4 by 90 minus d by 4. That is the result. No, not that. And this is we are taking about this. So you have to do d by 2 minus 1 minus 4 by 2. Okay. So about which axis you want to take? Suppose you don't calculate center error. You want to take about some other axis. Which axis comes to your mind? Which axis you would like to take? Suppose I take about this axis, I can take about this axis also. Then the moment will be very, very large. If I take about infinite axis, moment will be infinite. So the problem is that the moment depends on axis. How to solve this? So there has to be some axis. Now which axis we will take? One person is doing the analysis, another person is doing the design. So you have calculated moment from analysis. Now the other person is doing the design for that moment. So both should know that about which axis you have calculated, because moment depends on axis. So he should know about which axis you have done the analysis, so that the design is also done about the same axis. Otherwise there will be an error. So all the analysis are done about centered axis. When you have done matrix analysis, you make a computer model, you will protect a column by a line. Where is that line? At the center. So all the analysis are also done considering the centered axis, and that's why the design, we are doing the design. So design, or we are calculating the capacity. So capacity is also to be calculated about the same axis. Okay, but it can be any axis. If both of you decide that we will do at infinite, fine, you can do that. But the designer and analyst should be at the same page. They should be taking same axis. Because in case of column, axis matters. In case of beam, axis doesn't matter. Because you take moment of a couple about any axis, even axis are infinite, the moment will be same. So there it doesn't matter. In case of beam, we have not thought about axis, but when you are doing the same thing for column, then axis matters. So we have obtained 1 point on m versus phi curve. This is our m by dash and phi by dash. M by dash is bd square by 8 fy in this case. Okay, and phi y 3 by 2 epsilon y by 2. Please check that all of you have got it. Yes. Not final. Moment when the extreme compression fiber is having a strain is equal to epsilon y. That. So moment at first yield. And what is first yield? When the first fiber is yielding, and which fiber is yielding in this case? The extreme compression fiber is yielding. Tension fiber is not yielding. You got it? Right. So next, let's do it at 2 epsilon y, like we have done in the previous case. And then we will calculate at epsilon u. Give it your bending period. एक्सेल लोड होगा। हमने जहाँ सेक्शन लिया मोमेंट विल बी डिफरेंट एट डिफरेंट लोकेशन। एक सेक्शन का है at the moment we are doing a section analysis. So we are calculating the section characteristics. For material, the characteristic is F versus epsilon. For sections, the characteristic is M versus phi. And for structure, Q versus delta. So once we do this, then we will calculate Q versus delta for cantilever, with and without axial force. So one thing you notice here, that the yield moment has decreased. Okay. So if you have to plot PM interaction curve in case of steel rectangular section, you have plotted PM interaction curve already for RCC. You know. Okay. What do you think? How the shape will look like? Can you guess? In case of RCC, you remember, first the moment capacity increases and then it decreases. Okay, so the maximum P capacity is how much? BD Fy. And how much is the maximum moment? When only moment is acting. We are talking about yield moment, not the ultimate. Let's take yield moment at the moment. So BD square by 6. How you think it is going to vary in between? Will it be like RCC? First it increases and then decreases. Will it also be same? You can do it by taking different values of P. I have taken one value of P is equal to 0.25 BD, 1/4 of this. So this value I have taken. What do you see here? The M has increased or decreased? Decreased. So in case of steel, the interaction curve will not be like this. The interaction curve will be like this. Why in steel, why in RCC we get like this? Why we are not getting the same thing in steel? In case of steel?
In RCC, there are two components to take care of tension and compression.
Okay.
Steel and concrete.
Okay.
In steel, when compressive force is more,
So what those two components? Suppose I take aluminium and steel. Section cracks.
buckling problem.
बकलिंग नहीं है भाई, बकलिंग तो बाद में लगाते हैं जब लॉन्ग कॉलम डिजाइन करते हैं, एडिशनल मोमेंट लगाते हैं. There is no buckling. It is still section. This is PM interaction curve is the property of section, not property of member. So in section there is no length. So buckling is not coming into picture. Buckling comes into picture when we talk about the length, and then we look at those curves given in appendix in IS 456 and 800 both. Then buckling comes into picture. Here there is no issue of buckling because we are considering only a section. Section has zero length. Okay. So any one section will have PM interaction curve like this. Okay. In case of steel, the moment starts reducing as soon as you apply an axial force. Okay. But in RCC, when you apply axial force, initially the moment increases and then it reduces. Why? Why this behavior in these two materials? Two types of columns we are using. Why this PM interaction curve is so different? Suppose I have an aluminium column in which I have put steel reinforcement. What do you expect? Which curve it will follow? Similar to steel or similar to RCC? RCC?
Sir, I think in case of steel, the cross-section area is uniform throughout this, and in case of RCC, we are below neutral axis, we are taking as cracking, and we are concerned only steel area. Also, second reason is that in case of steel, models of elasticity, tension, and compression both are equal. In case of concrete,
Modulus of elasticity is equal.
No.
In compression terms.
okay, they will be equal,
No.
but area
Strength is different.
strength is different.
Okay.
Because we have anyhow match compression and tension for equilibrium. In case of RCC, that compression tension equality is matched by shifting of neutral axis due to changing.
That is done in any case. RCC also, when you apply axial force, the neutral axis has to shift.
And
Neutral axis has to shift towards tension side.
okay, and in case of steel, due to cross-section area property, we can manage
बहुत
strength.
सारी बातें आपने बोली, उसमें आंसर भी है. Whatever you have said, answer is there. But you have said many other things also. So I want you to be specific on the answer also.
Specific thing is that area of cross-section, uniformity of material.
Okay, so aluminium and steel. What about this? This is also non-uniform. So will it be like this? Will it be like RCC?
It is not RCC, like RCC.
Then, if non-uniformity is the reason, then this should have like RCC, because this is also non-uniform. So it means non-uniformity is not the reason. Reason is somewhere else.
So, in RCC, the concrete is taking care of the compressive forces. So, when in the steel, the compressive force is acting, so the strength is reducing because the compressive strength of steel is lesser than the tensile strength.
Compressive strength of steel is lesser than tensile strength.
Yes.
No, we have considered Fy in both. We have considered same stress strain curve in compression and tension for steel. For concrete, it is different. Have you heard about pre-stressing of steel?
No.
Pre-stressing of concrete, you must have done. But have you heard about pre-stressing of steel?
No.
Why not? Why don't we do pre-stressing of steel? We do pre-stressing of concrete only. We don't do pre-stressing of steel.
Pre-stressing, the object of pre-stressing is to ensure that the tensile strength should be in limit. In steel, we don't have a problem of tensile strength. Why should we go for pre-stressing?
Again, in that direction, but it's not the exact answer. Answer of a question cannot be question. Okay.
So, but pre-stressing of concrete,
Why pre-stressing is done only in concrete, not in steel?
pre-stressing of concrete is based on the tensile strength used by the steel. But not in the case of, we can't use the pre-stress for the steel.
Why not? So there also I want to use the strength of that tendon. Strength of the tendon may be higher than the strength of the steel. There is 250, that may be 1400.
But if we apply a load on steel members, it will lose their strength.
So when we will apply axial force on a steel member, actually it will lose its strength, not gain, which you see from here. As soon as you apply any axial force, the steel section starts losing its strength. On the other hand, concrete starts gaining. Why? Answer is very simple. Concrete is better in compression. Okay, so
Sir, in steel we are considering both sections in terms of compression, but in concrete we are considering only.
see what is the basic difference in the stress strain curve of concrete and steel? One thing is that one is non-linear, another is linear, and then other than that. The stress strain curve for steel is same in compression and tension. Concrete has very little strength, only 10%. in tension, and in compression it is much more. Okay, so what will you like? You will like that most of the concrete area should be in compression. That's bad. If more area of concrete is in tension, it's not being utilized. Okay, because that area in tension is giving you only 10% strength, and the area in compression is giving you 100%. Okay, so you will like that more and more area of concrete should be in compression. How you can achieve that? If you want more area of the concrete to be in compression, you can apply axial force. So when you apply axial force, then the stress you have seen just now, neutral axis will shift down, so area under tension will reduce. Okay, then you can ask, if I go on increasing the axial force, it should go on till the neutral axis goes reaches extreme tension fiber till that point. But it doesn't happen. It increases only up to a particular value of axial force. After that, why so? Why it reduces? Why doesn't it go on continuously increasing? With my logic, which I have given you, it should go on increasing with axial force. More and more axial force I apply, more and more area will be in compression. So better it should be, more moment it should take. So in compression also, concrete does not have infinite strength. Okay, if you are increasing the axial force, it is true that more area will be in compression and it will be affected. But at the same time, the compressive stress in the extreme fiber will also go on increasing. Okay, if concrete was having infinite strength in compression, then you go on increasing the axial force and bending moment capacity will go on increasing. But the strength in compression is also not infinite. So after a particular axial force, the crushing in compression starts taking. So this is that balance, so-called balance failure, where the crushing of concrete starts, and above this it is compression failure, and below this it is tension failure. So pre-stressing or axial force will happen only in the tension failure zone. Okay, in compression failure zone it will not have, because then the concrete gets or concrete starts getting crushed in compression. Okay, in case of steel, where compression and tension both are equally effective, if you apply axial force, you are losing something. Okay, so that's why here the axial force starts reducing the moment capacity immediately. Okay, so our interaction surface, interaction curve will be something like this in case of steel. Whereas in case of RCC, first it increases and then reduces. This is the effect on moment. Okay. Let us see what effect axial force has on curvature. So this we are trying to explain. So one thing you see that the moment, yield moment has reduced. Okay.
Little bit for steel. In case of concrete, we can understand it can.
Okay. Let's go back here. What we did today. So earlier, when it was subjected to bending moment only, that means no axial force. In that case, our neutral axis was here. And when this was epsilon y, this was also epsilon y.
Yes.
In compression and tension, same stress was applied.
Yes.
Now neutral axis has come down.
Yes.
So when it is epsilon y here, it is less than epsilon y.
Yes.
That means the material on tension side is underutilized.
Yes.
On compression side it has reached epsilon y.
Yes.
But on tension side it has not reached epsilon y. Here it is fy, here it is less than fy. So the material on tension side is not fully utilized. In case of concrete it was not like that, because tension capacity anyhow is very less. So that was already more than fully utilized. So there it was helping, here it is not helping. Rather it is causing underutilization of our material. If the stress curve in compression and tension is same. So if the strength in compression and tension is same, that axial force is not helping. Axial force, even if you apply little axial force, the capacity in bending will start reducing. Agreed? Okay. But think, if you can think from another angle, you can ask from another angle. Okay, so that's why the interaction curve in steel and concrete is different.
So in that case, if the compression fiber goes beyond Fy,
That's what we will do in the next step. We will check that also. That what will happen when epsilon y reaches epsilon u? Is the moment capacity increasing there or decreasing there? That also we will check. So let's first complete this. So this we have done. Everybody got this? My dash and phi y dash. Let's take 2 times epsilon y and check what happens to the axial force and bending moment. Sorry, axial force is given. What happens to bending moment and flexion? Or let us go directly to epsilon u. This is xu, this is d minus xu. Okay, let us say this is epsilon u here. So naturally here, this is less than epsilon. And how much is epsilon t? Again, epsilon u d minus xu over xu. Can you calculate the moment capacity now? What will be the stress distribution in such case? Can you plot the stress distribution? Strain distribution I have given, corresponding to this strain distribution, to plot the stress distribution. What is the stress distribution? Just the stress strain curve rotated at 90 degrees. Isn't it? The stress strain curve, the strain is increasing along x-axis. Here the strain is increasing along the y-axis. So that curve is only to be rotated at 90 degrees. That's it. Yes. Right. This line will be same because this line is what? It is E. This E will be same. This line will continue like this till it will be okay. You can make an assumption and then check it. So that will depend on the value of D. Suppose, value of X. If X is very, very large, let us say just very close to D, then F2 will be, Fy will not be D. Okay, it will still remain linear. If X2 is in between, okay, then, so let us first assume, we already know that X2 is something like 230.
Yes.
Okay, it's not going to be 0.99 D under this axial force of 0.25 VDFY. So can you calculate C and D and then calculate the value of X in this case? क्या करता है? ये क्या है? मॉडल से क्लासिटी अप्रोक्सीमेटली कर सकते हैं, अप्रोक्सीमेटली कर सकते हैं। हाँ राइट, तो आप एप्सिलॉन वाई और एप्सिलॉन यू का रेशियो पता है? कोई भी कर लो, उसका जो म्यू पाई म्यू एप्सिलॉन है होगा। Now first we draw qualitative, how will it look like, then we will do quantitative. Yes, depending on where is the neutral axis. So depending on the neutral axis, it will remain or it may become like that. Both possibilities are there. So where do you expect the neutral axis? For this, we have already calculated for m by dash. So the neutral axis is somewhere to the. So in that case, how will it look like? So it will look like something like this. This will also be Fy, this will also be Fy, okay? And this depth you can determine. But when we know the strain has reached epsilon u, okay, it is, we have seen even much before reaching epsilon u in the previous case, that it is as good as the full section plastified. Okay, and we have calculated the error. Error was less than 0.5%. Okay, so we can simplify our calculation if we assume this, and later on we will check. So let's first assume the full section has plastified like this. It will make error, but that error is going to be very, very small. Let's do that and then calculate C and T, equate that equal to P and calculate XU in this case. So this is the additional area we have added. At large strain in extreme fiber, this added area is small and the contribution in bending moment is even small. This added area. It is making less error in bending moment. This we have seen yesterday.
So here we are assuming that epsilon T has more than E.
Yes, I have assumed that it is more than that. You can check it later that whether this assumption was correct or not. Because on what it will depend? It will depend upon the value of XU. So once you will determine value of XU based on this assumption, later on check the value of XU and the strain diagram that whether this assumption was okay or not, which I have assumed. So first we are assuming here that epsilon D is greater than epsilon y. Of course it will be less than epsilon u, that we know. It is going to be less than epsilon u, that we know. But whether it is greater than epsilon y or not, that we have to check. That's why we are plotting moment versus curvature, not P versus curvature or P versus. P is constant. At constant axial force, we are increasing the moment, okay, or rather increasing the curvature and then checking. So it is a displacement control. Yes. Have you calculated action?
How
It is not needed. If you go with my assumption, this is not needed. But if you want to calculate, you can calculate it. This is XU. How much will be this? Epsilon y by epsilon u times x. Epsilon y by epsilon, this is 1 upon mu. Okay. How much was mu in case of steel? We have calculated of the order of 100. Mild steel. So it is only 1/100th of that. Very small. So we can ignore it.
So we consider full XU.
We will assume that the full section is classified, and we have seen yesterday that it doesn't make much error. The error is less than 0.5%. Yes. Who is calling? Okay. I'll call you. Have shifted somewhat. So XU is, in this case,
9 by 16.
huh?
9 by 16.
9 by 16. 5 by 8. You can calculate MU and phi. Okay. So I think we will continue from here when we meet on Monday. Tuesday. Tuesday is 24th. 24th I will not be able to take class because I have to take interviews at IIT also. I will be in office only, it will be online interview, but it will be going on. So Tuesday's class will not be there, Wednesday we will be. So now we are Wednesday 50. So what I can do is Monday 23rd. Monday's class I will take. Taju will take the class on Tuesday. So I will exchange with Taju. This Monday class I will take. So Monday 4 to 6 we will meet. And there we will continue from here. But try to see. I have not done anything new. Everything you have already done. Okay. We are only revising.